Hey guys and gals, what we have here is our very first intro video that I'd like you to look at before we get into class, which is actually tomorrow at 8 in the morning. So if you don't see it, you don't see it, but I'll put it on email. Hopefully you do see it. Anyway, the first section, this first chapter is about integration techniques, and this first one is about what they call integration by parts. I didn't write it anywhere, so I'll write it now. It's about integration by parts, or integration by parts. And I'm going to do this kind of quick and I'll explain it in class, but basically as an example of some cleverness that happened generations ago, let's say, let's take a look at the derivative of x times sine x. And of course, to do that, you have to do the product rule from Calc 1. Okay, and when you do it, you get this guy right here. And then I say, rearrange it so that we're solving for x cosine x, and we're to here right now. Does that make sense? Okay, then integrate each side. Someone had a clever idea. He said, you know what? The integral of x times cosine x, which we don't know how to do from Calc 1, can be written as the integral, watch this, of the antiderivative, okay, minus sine x. So what I'm doing is I'm integrating each side. When we do that, okay, what happens is the antiderivative and the derivative cancel, and you've got this statement right here. The integral of x cosine x is equal to x times sine x minus the integral of sine x, which means that, look at this, we have a new integral. We have the integral of x times cosine x. We could not do that in Calc 1. There is no product rule for integration. But notice how this thing started. It started with product rule. So in a sense, integration by parts allows us to, what, reverse the product rule in a way. So there's a pattern here. Pretty cool stuff. And you can always check to be sure that we did the right thing by deriving the right-hand side. Have you ever checked your integrals before? Let's do it. If we derive with respect to x, our answer, which is x sine x plus cosine of x plus c, and start deriving this thing, boy, my handwriting is ginormous. I'm getting used to this. Well, I have a product rule which says, okay, 1 times sine x, and then plus x times derivative of sine is cosine of x, and then the derivative of cosine is negative sine x. Of course, derivative of c is just 0. And lo and behold, we get x times cosine of x. You know what? That's a good thing. All right? So it is the antiderivative, and this new way of doing things is acceptable, at least with this example. What I'm going to do is I'm going to show you this. This is what I always quote. This integral of u dv is equal to uv minus the integral of v du. Well, what the heck does that mean? I better put this in red. Okay, so u is the function x. And if I derive that, du is dx. Okay, I'm just showing you how the pattern works. And then the rest of it, which I'll put in maybe a different color, the rest of it here is dv. dv is cosine x dx, so that when I integrate to find v from dv, we get, what do we get here? Integral is sine. It's sine x. So the pattern that we see here, I hope you see this, is over here, this guy is u, and then way over here, dx is du, sorry. And the sine x is v. I should have done that in blue, so I'll try to do that in blue. So the sine x is v, and the sine also here is v. So we have u times v minus the integral of v times du. This pattern here we're going to use on this next example, and we'll be done with this video, believe it or not. So you can pause anytime. So here's our example. It says, let's find the integral of x squared times e to the x dx. It's another example of a, say, a polynomial or rational expression, whatever, times a transcendental function. So those guys are pretty obvious, but in lecture you'll find that they're not all obvious at all. So what I'll do in this case is I'll just go, I'm going to break this apart. I'm going to let u, this is what I really wanted to show you how to do these problems, let u equal x squared. The good news about that is when I go for du, it breaks down to 2x times dx. So yeah, oftentimes I want to choose a function for u that when I derive it, it gets less complicated. It doesn't always go that way. Then dv is the rest of the expression, e to the x dx. And when you integrate both sides, you just get e to the x like so. Okay, so using the pattern that it's equal to uv minus integral v du, which is nice to remember, we get that the integral of x squared e to the x dx is equal to uv, and I tend to do this on the board with another marker, u times v. Okay, so let's write that in red. It's x squared e to the x minus the integral, I'll do this guy in, I don't know, blue. Oh, I don't want that. I'm going to be doing this the whole time. Okay, let's do that, okay. And it's going to be v du. So minus the integral of 2x e to the x dx. Okay, you'd like to say we're done, but we still cannot integrate 2x e to the x. We're going to do it again. Okay, so we're going to say, for this case, for this integral over here, let u equal 2x. When I derive it, du is 2 dx. And the other guy, let dv once again be e to the x dx. Integrating v, you get e to the x. So I'm going to put those pieces together. We're going to get a final answer coming up here. Okay, so our integral is equal to the first part, which is x squared e to the x minus, watch out, big old bracket. I'm going to write uv, which again, this time it is u times v is 2x e to the x minus integral of v again times du, which is just 2 e to the x dx. You know what? Integrable. We know that guy from Calc 1. So we have an answer. It's coming at you. The integral of x squared times e to the x dx, using integration by parts, allows us to find this guy, x squared e to the x minus 2x e to the x, and then here we go again, minus 2 e to the x. Since we're done, tack on the plus c, and that's a more extensive example of integration by parts. And that's the end of the video. You're going to have to practice this one over and over and over again to get successful. All right, I will stop the recording. Ta-ta.